The colossus of the plains looms on the horizon. This rotating storm, called a supercell, is equal parts beauty and danger. It's a testament to the raw power of nature, but also the incredible complexity of our atmosphere. How do these beasts come to be? In this video, we're going to find out right after this. Supercells are the most severe thunderstorms on the planet. They produce the biggest hail, the most violent tornadoes, and oftentimes some of the most violent wind gusts. Supercells are also relatively rare. Some scientific estimates say they comprise of less than 1% of thunderstorms, yet they're responsible for a huge amount of the damage thunderstorms cause each and every year. But how do these beasts form? Most thunderstorms require lift, moisture, and instability to form. Lift occurs both at the surface and high up in the atmosphere from boundaries like cold fronts and from low-pressure systems aloft. Moisture is often sourced from the Gulf of Mexico to the south. A fetch of high-quality moisture frequently precedes severe storm development by over a day in advance. Finally, instability is the last ingredient. An atmosphere becomes unstable when the air is much cooler above the surface than below, because warm and moist air tends to rise. If the air aloft is significantly cooler, storm clouds can form. All of this leads to a thunderstorm, but for a supercell, you need one more key ingredient: wind shear. Wind shear is both the turning and increasing wind speeds with height. For supercells to form, the winds must turn significantly from the surface to several miles up in the atmosphere. Oftentimes, as a storm system approaches Tornado Alley from the west, the wind is out of the south at the surface over the Great Plains. The winds from that storm system are often out of the west or southwest. This turning with height, along with increasing speeds, allows for thunderstorm updrafts to organize into supercells. This is achieved by both tilting over the updraft and giving the updraft rotation. Both of these lead to a long-lasting cell that can produce the most severe weather.
It was solid all the way over to here, but no, it's turkey towering and blowing off. So yeah, that isn't nearly as impressive as what I thought.
It's a warm day in Tornado Alley, and the storm chase team, the Tornado Titans, is in position watching storm towers grow. These initial towers are the precursors to storm formation, and they offer tantalizing clues as to what the atmosphere is brewing up. At this stage of the chase, storm chasers are looking for storm towers that are wider and growing larger. Some towers are skinny and are being cut off by the cap, a layer of warm and dry air aloft that keeps air from rising. Others, though, are beginning to build into storms, but we don't quite have a supercell yet. Our chase team is sitting just to the east of a developing cell, watching for signs both visually and on radar that this storm is beginning to rotate. One of the first visual cues that the wind shear is good enough for supercells is the presence of a large rain-free base. At the very least, this shows that there is enough vertical speed shear in the atmosphere to tilt an updraft over. If the base begins to round, and if scud begins to rise up into the storm, a storm chaser can be near certain the storm is a supercell. But storm chasers don't just have to rely on visual cues. Today's storm chasers can also use real-time radar to gauge a storm's progress. Without wind shear to organize it, the average storm cell will appear more like a loose collection of blobs in a region. A supercell looks different. Typically, a supercell will begin to take on the shape of a kidney bean, especially early on in the storm's life cycle. This curved look is often the first sign on radar that a storm is rotating. Additionally, a velocity scan aloft can tell you if a storm is indeed spinning. The classic red and greens together mean a storm has acquired the ability to rotate. With radar and visual cues, storm chasers can piece together the mystery of if a storm is a supercell. A supercell has indeed formed, and the storm's mesocyclone is getting stronger. Next in this series, we'll be taking a look at the mesocyclone and how it separates a supercell as the titan of thunderstorms.